Welcome to Chapter 6, Work and Simple Machines. This chapter connects directly to energy from Chapter 5. Everything we discuss here is about energy and how it moves from one object to another, how we measure that movement, and how we use the tools to make moving things easier. As we go through this chapter, focus on energy transfer, force, distance, and mechanical advantage. Those ideas will show up on the test. In science, work does not just mean effort. Work is the transfer of energy that happens when a force makes an object move. Two conditions must be met. A force must be applied, and the object must move in the same direction as the force. If either of those two are missing, then scientifically speaking, no work is done. Look at the example of lifting a barbell. Your arms apply an upward force and the barbell moves upward. Because force and motion are in the same direction, energy is transferred. That means work is being done on the barbell. Now imagine holding that same barbell still above your head. Your muscles are working hard, but the barbell is not moving. Since there is no movement, no energy is transferred to the barbell. Even though it feels like work, scientifically, no work is being done. If you carry the barbell while walking forward, your force is upward, but your motion is horizontal. Because the directions do not match, there is no work being done to the barbell. Direction matters when calculating work. Anytime work happens, energy is transferred from one object to another. Energy does not disappear. It moves. Understanding that work equals energy transfer is critical for this chapter. When you carry a box upstairs, your body converts chemical energy into gravitational potential energy in the box. That increase in potential energy proves that work was done. The formula for work is W equals F times D. Work equals force multiplied by distance. If either force or distance is zero, work is zero. Force is measured in newtons, distance is measured in meters, work is measured in joules. 1 joule equals 1 newton times 1 meter. If you apply 100 newtons of force and move something 5 meters, you multiply 100 times 5 to get 500 joules of work. If you know work and distance, divide work by distance to find force. Always rearrange the formula carefully and check your units. If you do 600 joules of work on a box to move it 3 meters up a flight of stairs, how much force did you apply? 200 newtons up. Work only happens while the force is being applied. If you push something and let go, work stops once contact stops. Power is how fast work is done. Two people can do the same amount of work, but the one who finishes faster has more power. The formula for power is P equals W divided by T. Power equals work divided by time. Power is measured in watts. 1 watt equals 1 joule per second. This means 1 joule of energy is transferred every second. If 600 joules of work are done in 10 seconds, divide 600 by 10 to get 60 watts. Energy can also be found using power times time. E equals P times T. So if a 150 watt TV runs for 1 hour, convert the hours to seconds first. 1 hour equals 3600 seconds. Then multiply power by time. The answer is 540,000 joules. In Chapter 6, Section 2, we will learn about machines and what a machine is. Machines are a device that makes doing work easier. It does not reduce total work, it changes how the work is done. Machines make work easier by increasing force, changing direction of force, or increasing the distance over which a force is applied. The second way that machines can make work easier is by changing the direction of the force applied. A pulley is a good example of this because with a change in direction, many objects are easier to move. The third way that work can be made easier is by increasing the distance at which the force is applied. An example would be a rake allowing you to move more leaves because it is much easier than it would be otherwise. Think of a car jack. You move the handle a long distance to lift the car a small distance. The trade-off is distance for force. In an ideal machine, work equals work, or work in equals work out. No energy is lost. When pushing a piano up a ramp, you apply less force but over a greater distance. It is the same whether you push the piano up the ramp or lift it straight up. Pushing requires less force because the ramp has a greater distance. A wedge changes the direction of a force. An axe converts a downward swing into an outward splitting force, much like the car jack. A pry bar increases force because the input arm is longer than the output arm. Input force is what you apply. Output force is what the machine applies. Those are the two forces involved when you do work. In real machines, friction causes some energy to be turned into heat, or thermal energy. This makes output work less than input work. For this class, we will assume that no friction and perfect energy transfer exist for all machines, meaning that work in will be equal to work out. This is not true to the real world. Mechanical advantage equals the output force divided by the input force. If the result is greater than 1, force is multiplied. This is known as mechanical advantage. Efficiency equals work out divided by work in times 100%. Efficiency tells us how much useful work we get. Reducing friction increases efficiency. Oil and smoother surfaces help machines operate better. Chapter 6, Section 3 will be all about the simple machines. Simple machines perform work only in one movement. A simple machine is a machine that does work with only one movement of the machine. There are 6 different types of machines: levers, pulleys, wheel and axle, inclined plane, screw, and wedge. A lever is a rigid bar that pivots on a fulcrum. Depending on where the fulcrum is on the arm will depend on the type or the class of the lever. There are 3 classes of lever. First class, the fulcrum, is located between the input and output forces, and the force is always in the opposite direction of the input force. So if this is pushed down, this is pushed up. Second class, the output force is located between the input force and the fulcrum. The output force will always be greater than the input force. Third class, the input force is applied between the output force and the fulcrum. These increase speed or distance. A screwdriver opening a paint can is a good example of a first-class lever. The rim of the can acts as the fulcrum, and the lid is the load. A good example of a second-class lever would be a wheelbarrow. In this case, the wheel acts as the fulcrum. A baseball bat is a good example of a third-class lever. The fulcrum of the lever would be your non-hitting hand. The ideal mechanical advantage of a lever equals the length of the input arm divided by the length of the output arm, or Ln divided by Lout. A pulley is a grooved wheel with a rope, chain, or cable running along the groove. A pulley can be thought of as a modified lever. The axle in the middle is the fulcrum, and the rope on either side is the input and output arms. A fixed pulley is attached to something that doesn't move and will only change the direction of the force. If there is a 100 Newton weight, it will take 100 newtons of force to lift it. A movable pulley reduces the force needed because multiple rope segments support the load. One end of the rope is fixed and the wheel of the pulley is free to move. This lessens the force needed to lift the weight because it fixed the end provides half the force. This means that a movable pulley will have a mechanical advantage of 2. For a block and tackle system, count the rope segments supporting the load to find mechanical advantage. The IMA of a pulley system is equal to the number of rope segments that supports the weight. In this case, 4 rope segments equals an IMA of 4. A wheel and axle consists of 2 rotating parts at different sizes. A wheel and axle is a simple machine consisting of a shaft or axle attached to the center of a large wheel so that the wheel and axle rotate together. Doorknobs, screwdrivers, and faucet handles are all examples. The ideal mechanical advantage of a wheel and axle is the radius of the wheel divided by the radius of the axle. It is a form of a modified lever. So you would divide the radius of the wheel by the radius of the axle to find the ideal mechanical advantage. Gears are wheels with teeth that interlock to change force or direction. Because of these teeth, gears can change the size or the direction of the force. An inclined plane is a ramp that reduces force by increasing distance, commonly referred to as the hypotenuse. The IMA is the length of the slope in meters divided by the height of the slope in meters. The screw is an inclined plane wrapped around a cylinder. This increases the distance that the force is applied. A wedge is an inclined plane that changes the direction of force. It is often used for cutting or splitting. A knife or an axe blade are good examples. Most real machines are compound machines, meaning they combine two or more simple machines working together. Understanding how these simple machines function will help you recognize them on the test.